The representations that we've used so far are good for various different things, but they won't work for every scenario. You know, sometimes a pie chart is not the most appropriate choice, or a bar graph is not the most appropriate choice. For this example here, if we're collecting data and we have 2,000 temperatures at the same time each day, and we want to recognize what is the lowest temperature, the highest temperature, the median of the first half of the month, and the median of the second half of the month, because we're trying to analyze the weather patterns. None of the things that we've done so far, like the stem and leaf, the bar graphs, the pie chart, the line graphs, none of these are really going to give us that information in a really quick way to just look at it. I mean, can you imagine trying to make a stem and leaf with 2,000 temperatures? It would be annoying, and then it would be too much to look at to try to figure anything out. So if you're talking about kind of a large set of data, or if you want to see the median and the range, then we're going to use a box and whisker plot. Okay. Now this does not show us the average. It shows us the median. It shows us the ranges. We can see if there are outliers and things like that. All right, so a box and whisker plot is also known as a box plot. So if you hear box plot or you hear box and whisker plot, they're the same thing. Most people probably say box plot because it's shorter. Okay, so a box plot graphically represents data. By plotting 5 specific numbers. Okay, and these 5 specific numbers are known as the 5-number summary. Actually, I think I should read that up. Okay, so the 5 numbers that we want to plot, the first one is we plot the lowest number, otherwise known as the minimum value. Okay. The second number we plot is what's called the median of the lower quartile. Which I will explain how to find that in a moment. This is called Q1. And then we plot the median of the entire data set. That's Q2. And then we plot the median of the upper quartile. Which is Q3. And then finally we do the highest value or the maximum. Quartiles. Q stands for quartile. So this is quartile 1, quartile 2, quartile 3. And remember, quartiles is a quarter, which is 1/4. So we're talking about 1/4 of the data. So the first quartile, Q1, gives us the line where 1/4 of the data is. And then Q2 gives us the next fourth. Q3 gives us the next fourth. And then once we get to the maximum, that's the last fourth. Okay, so 50% of the data is in the box. more information about the data set. Gross. Okay, so information about the data set that can be determined just looking at it really quickly. First of all, we can see where the median is, and the median of the bottom half and the median of the top half. That's really quickly. We can see the max and the minimum really quickly, but also we can figure out if the median is located at the center of the box, the distribution is approximately symmetric. So if we come in and we have our box, I didn't mean for that, but okay. And our median, you guys say that's about the middle? Is in the middle, and we have our whiskers off to whatever side. Then we're approximately symmetric. This would give us a bell curve. If the median is located to the left of the center of the box, so here's our box, and our median is left of center, you have our whiskers, then the distribution is positively skewed. And like a curve or a histogram, instead of being symmetrical, it would be like that kind of thing. Let me make that actually like that. So we have positive outliers pulling our data over that way. It shouldn't go that far, kind of an idea. And then if the median is located to the right of the center of the box, so we're over here somewhere, we're negatively skewed. So we've got like a bunch of data over here on the lower side pulling us. So we should not be that far. Yeah. So it's kind of the same thing as we were talking about with the histograms, where or the curves where they're pulled, and it's like the opposite of where the bump looks. So it's the same thing here. If our line is on the positive side, we have these negative values pulling us, like outliers pulling us further than we should be going in that negative direction. Does that make sense? Okay. We can also find things from the whiskers, and if we throw in some boxes, right? If the whiskers are about the same length, we're symmetric. So that's, again, a bell curve looking thing. We have a symmetric distribution. If the right whisker is longer than the left whisker, I'm making it really obvious, then we're, again, positively skewed because we have some outlier over here pulling our data too far on the positive side. Yeah, so this again would be that kind of a curve that, yeah, does like that. And then if the left whisker is longer, we're negatively skewed, which again is going to be like on our distribution if the curve would be over here, because we have some outliers on the negative side pulling our data further than it really should be going. Okay? And the length of the whiskers also gives us information about how spread out the data is. If the length of the whiskers is really short like that, we don't have a really far spread. But then if we have these really long whiskers, we have a really big spread. Because the whiskers tell us from our minimum to our maximum value. So that's why we can see how spread out the data is. Like I said at the beginning, we use a box and whisker a lot of times when we have a lot of data. Like in that first meteorological, can't say that word, example, there were 2,000 temperatures taken, right? And when you have that much different data, that many different data points, making a line graph or a histogram or bar graph or stem and leaf, it's too much data to try to put in a manner that'll be easy to look at. So we use the box and whisker because we can see the center of the distribution. The center is the box. That's where most of the data is. 50% of the data is in the box. So we can see the center. We can see the range because that's the ends of the whiskers. So we can see that really fast, no matter and it doesn't take into account if there were 20 data pieces or 6,000 data pieces, it's still going to be just as easy to look at. We can see where the medians are, which the median gives us like that measure of central tendency. So most of the data is going to be right by that line. We can see if we have outliers really quickly, like if anybody over here shouldn't be taken into consideration because they're an outlier. So it's really good to look at if you're analyzing data. So here's the thing. There are values that are called outliers, and they are extremely lower or extremely higher than the majority of the data. And we will figure out how to calculate to determine what numbers are and are not outliers. Here's how outliers occur. The value is made or comes from an error in measurement or observation. So this is researcher error. Oops. Okay. The value could be an error made by the researcher in recording the value. Like when I type it down, instead of putting in 2.15, I put in 21.5. Okay, so, typo. Oops. So you always want to double check when you see outliers to make sure you recorded the data correctly. The value could be obtained from a subject not within the defined population. So for example, is like if I was looking at math test scores and I was doing 12th grade exams, but some 11th grader took a 12th grade math test, I shouldn't include them in the study population, because 11th grade, like if you were talking about, if it wasn't individual subjects, but if you're talking about like levels, an 11th grade level should not be able to pass a 12th grade final exam, right? So their score is going to be skewed. So, you want to, again, this is another oops. You want to double check your data. Now, number 4. This is the one that's hardest to decide what to do. A value could be one that is legitimate, but it's extreme and compared to other values in the data set. So let's say we're measuring student heights throughout the school. And let's say, hypothetically, Shaq goes to our school. He's not going to fit in with our data set, right? Because he's, what, 6'7" or something? I don't know. He's really tall, right? Really, really, really tall, and everybody else is really average height. We have some tall people, some short people. We have average heights, and then he would be like extreme tall. So this happens, but sometimes, it's not very often, but it's outside the norm. And there are people whose data will be outside the norm depending on what you're asking about. Whether that's like demographic information, age and weight and height and race and location, or whether it's like number of hours you work per week. There's some crazy workaholics that put in, like tons and tons of hours. So, like they would be outside the norm, because the norm is somewhere between 30 and 50. So if you have an outlier that's present because of an error in measurement, if you can't correct it, you eliminate it from the data set. Because if it's an error, it can't be included. Okay? If it is a legitimate value, like I said, like we're measuring heights and Shaq happens to go to the school. Yeah, well, he's really tall. So you have to decide, as a statistician, you have to decide whether or not to include him in your data set. He is outside the norm of heights. So if you're doing a study on, the heights of people that go to this particular school, he's going to skew your data. So you have to decide, do you put him in there and have him skew the data, or do you keep him out of the sample? That's a personal decision, yeah. Yeah, he's like 9 billion feet tall. Yeah, something like that. something like that. All right, so we're going to figure out how to find outliers. Okay. First, we have to organize the set of data and find Q1 and Q3. All right, so I'm going to just make up a data set. Okay. 7, 8, 23. All right, I'm making up data. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, I counted 2 and 23 is 2 and 3 is 23. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I have 9 data pieces. So I have them in order already. So the first thing we want to do is we want to find Q1, Q2, and Q3. You find Q2 first. Okay, that's our median. That's the median. Okay. So, is it 5? Yep, it's 5. Okay, so here's Q1, Q2, I mean, because that's our median. Now to find the median of, or Q1 is the median of the first half of the data. Yeah, so it's going to be in between 2 and 3. So it's going to be 2.5 is Q1. And then Q2, 3 is going to be between 7 and 8. Yeah. So it's not hard to find Q1 and Q3. You just have to find Q2 first. So you find the halfway point, and then you find the halfway point on this side and the halfway point on that side. So not too bad, right? Yeah, 1 would be the end of the whisker, and 23 would be the end of the other whisker. Now, excuse me, to find, so we have Q1 is equal to 2.5. I was meant to put that in this spot, but whatever. Q3 is equal to 7.5. Okay, now we're going to calculate what's called the inner quartile range. So we take the third and we subtract the first. So 7.5 minus 2.5 is equal to 5. No, the median is, well, okay, in this case it did, but normally it won't. Okay, here I'm just going to put not the median. Okay, this is the range between the largest quartile and the smallest quartile. So how many numbers are in between them? Yeah, so we're saying how much space is in between them. There's 5 spaces between them. That's why it ended up being 5. Yeah. Okay. It would have been different. Yeah. So this is not the median. It's not even a number in the list necessarily. It's the number of numbers between the lowest number and the highest number. Okay. So now we have to multiply this by 1.5. Okay, so 5 times 1.5 is 7.5. Okay, so yeah, I picked really bad numbers because I'm getting them over and over again. Okay, then I subtract this from Q1. So Q1 is 2.5. So minus 7.5 is negative 5. And I add it to Q3. So 7.5 plus 7.5 is 15. Okay. I take this IQR. I do IQR times 1.5. Then I subtract it from Q1 and I add it to Q3. Yeah. Hold on. No, I don't. I subtracted. Up here I did Q3 minus Q1. That gives me the interquartile range. And then I take that and I multiply it by 1.5. And then I subtract it from Q1 and I add it to Q3. I'm trying to find the outliers. So I need to find data on either side that anything past that is an outlier. That's 5 times 1.5.
Yeah, and that's what we use for the second column. We use that number.
Yeah, this is here.
Okay, that's what was confusing.
Okay.
That was Q3 or that number.
No, no, that's Q3. I'm writing it right here.
I see.
Okay, so times 1.5 times the IQR. Now that tells me -5 and 15. Okay, hold on one second. Anything below -5 is an outlier. Okay, we don't have anything below -5 up here. Anything above 15 is an outlier. So in this case, I threw 23 in there. So 23 is an outlier. So what this gives me is the range of normal. The lowest normal and the highest normal, that's what that gives me. And then anything outside of that, either lower or higher, is an outlier. Does that make sense? So if we were to put this like in order again, so I have a 1, 2, 3, 4, 5, 6, 7, 8, 23. Okay, and over here is going to be -5, and right here is going to be 15. Everything between these two numbers would be considered normal. And anything over here or over here would be an outlier. Now that doesn't mean our data is going to go all the way to those ranges of what would be considered to be still normal. But if it can hit that far and still be considered normal, anything past that is an outlier. Yeah, anything from 15 on, so even 15.5 would be an outlier. But 15 is not an outlier. Anything, yes. 15 is the wall that you don't want to cross. Does that make sense? And then on this side, -5 is the wall that you don't want to cross. No, you need to find where they are because of this. If you're doing statistical analysis, outliers skew your data. And so you need to identify outliers to determine if they're a mistake or if they're legitimate, but like an extreme case, because sometimes like those extreme cases, because they are extreme cases, do they really fit in with your normal population? So should they be part of your analysis or not? You have to make that judgment call. So like if I was doing the example where I was saying before, like Shaq's height, I would go ahead and include him in the height study because I'm talking about the heights of the students at the school. But if I was talking about average hours working per week, and there's some like crazy workaholic that works like, let's see, hold on, let me figure out how many hours are even in a week before I give some number that can't be possible. Okay, there's 168 hours in a week. Let me say I find somebody that works 120 of those. Okay, they work 120 hours a week, and it's legitimate. They're working 120 hours a week. Am I going to include them in my study of the average amount of hours per week somebody works? No, I'm not. They're an extreme case, and they're going to skew my data and make my results all kinds of wrong because most people, like 99% of the population, does not work 120 hours a week out of 168 total hours in a week, right? So that's what I'm saying. So you want to make that judgment call at that point. But that's why you have to know what the outliers are to know if you need to take them out or not. Yeah, exactly. So, okay, we're going to look at some, okay, here we go. We're going to list the 5-number summary. We have the minimum here, Q1, Q2, Q3, max. Yes. No. Skewed negative. Okay. So our minimum is 4. Q1 is 6. Q2 is 9. Q3 is 10. And the max is 12. Okay. They didn't ask us, but we'll just see if there's an outlier here. So for the outlier, I'll do Q3 minus Q1, so that's 10 minus 6, which is 4. I take 4 and that's not a 9. I don't want it to look like a 9. 4 and I multiply it by 1.5, which should be, that's just the number, that's the constant. Okay, so then I take Q1, so that's 6 minus 6 is 0. And then I take the Q3, which is 10 plus 6, which is 16. And so any outliers would be less than 0 or greater than 16. I'm at from 4 to 12, I have no outliers in this data set. Okay? Yeah. Does that make sense now? A little bit better? Okay. Q1, oops, not Q1, sorry. Minimum is 225. Q1, 250. Q2, 300. Q3, 325. Max is 350. Not too bad. Do you want to see if there's any outliers again, just to get more practice at it? Okay, so I've got 325 minus 250, which is 75, right? Yeah, 75. I take 75 and I multiply it by 1.5, which is 112.5. And then I subtract that from Q1 and I add it to Q3. So I get 137.5 and 437.5. So since I'm inside of that area, we have no outliers. So far okay? Let's talk about the skew on this one. This one is, we're off to the right a bit, so we're negative skewed. Right, so we've got some numbers over here pulling us further this way than, or this way than we should be. Yeah. Yeah. Any questions on that one? Okay. Don't know why we had to have all of this number line, but we did. No. I don't know. I thought you did. What was the skew on this one? Positive, because we've got the median. Yeah. So positive skew. So that means we have some numbers over here that are pulling us that direction. And if we check for outliers, we've got 95 minus 70, so that's our range is 25. Multiply that by 1.5, and you get 37.5. 70 minus 37.5 is 32.5, so that would be over here somewhere. And 95 plus 37.5 is 132.50, which would be somewhere over there. So we have no outliers. So we're skewed, but no outliers. Any questions so far? If it's in the center, it's symmetric. Yeah, it's not skewed at all. It's just symmetric. So if we have in the box, right, center is symmetric. Over here is positive skew. And over here is negative skew. Okay, so opposite of which side it's on.
Yeah, use the median of it.
Yeah, use the median. Use the middle of the box. Like this would be where the middle of the box is, about there, and then just see which side of the box, like the middle it is. If it's almost on the middle, we'll just call it symmetrical. Like if the middle is here and the line is right there, that's not skewed. Okay, just call that symmetric as long as it's all about in the middle. Good? All right. Now we are going to construct a box plot on our own now. So first we have to do is put the numbers in order. The numbers have to be in order for us to find the median and then the median of the medians. So we have 204, 213, 222, 250, 269, 287, 288, 343, 547, and 650. Okay. Then we have to find, let's put it up here. Step 2, find Q2, then Q1 and Q3. Okay, so you have to find that median first. So I just start doing this until I run out of space. Okay, there's my median. It's going to be in between those because I have an even number of numbers on either side. So Q2 is going to be 269 plus 287 divided by 2. So that is 278. Okay, so there's Q2. And then for Q1 and 3, Q1 is 222. And Q3 is 343. So far okay? Alright, here's our min, and here's our max, and that's our 5-number summary. 1, 2, 3, 4, 5. We've got our 5 numbers. Okay, the next thing we need to do is we need to make a number line, basically. So do you have to stick every single number on the number line? No, you don't. But you want things to be relatively spaced out. So if this is 200 and this is 650, I need to space this pretty accurately. So what I do is I go ahead and I make a line, and I call this my minimum, 204. And I'm going to call this my maximum, 650. Or you can actually draw out a number line and have everything evenly spaced. Okay, I have 222, 278, and 343. Between 200 and 650, the halfway point is 450. Or sorry, no. Whoops. 425. So exactly halfway between here is going to be 425. I don't have that number, so I'm going to go halfway again. because I'm just trying to space it out correctly because we need to be able to see if it's skewed or not. So between 425 and 200 is 337, and between 425 and 650 halfway is going to be 537. Okay, so that's giving you my scale a little bit. So here's 337, so 343 is not going to be too far off of that. So I'm just going to put it about there. Okay, and 222 is going to be closer over here. And 278 is going to be maybe here. Okay. These three numbers get the box because that's Q1, Q2, and Q3. And then my whiskers, I have a short whisker here and a really long whisker over here. This tells me I am positively skewed. Right? Because I'm pulling way over. Now, are there any outliers? Well, let's check. I take my range, which is 343 minus 222. I'm guessing that there is going to be an outlier over here. You know, that's just my guess. I take the 121, I multiply by 1.5. It's 181.5. If I do 222 minus 181.5, I get 40.5. Obviously, I'm not even going anywhere near that far down, so no outliers on the lower side. But then if I take the 343 and I add 181.5, I get 524.5. If I come over here, I have two outliers. This is what's making my data this extremely positively skewed. If I were to take the outliers out, I would end my my box would end here, or my whisker would end here, which would change the position of my box. Does that make sense? So you can see that taking this data out, the outliers out, would really change your distribution. Is that good? Okay, we're going to check for outliers again. We have to put these in order to be able to check for outliers because we have to find Q1 and Q3. So I'm just going to put them in order really quickly. Okay, so here's Q2, Q1, and Q3. Okay, Q3 minus Q1 is 22 minus 18, which is 4. 1.5 times 4 is 6. 18 minus 6 is 12. 22 plus 6 is 28. 5 is less than 12, so 5 is an outlier. Okay, so we have one outlier to the small side. So far, okay? So 5's our outlier. If I do the next set, put them in order, guys. Shh. Okay, and 42. Finding the median. There's our median, and then our first quartile is between 13 and 14, so it's 13 and a half. And our next quartile is between 19 and 26, which is not so easy to do in your head necessarily. So I add them together and I divide by 2 and I get 22.5. Okay. So then I subtract those. Okay. And that gives me 9. 9 times 1.5 is 13.5. So I'll add and subtract. So when I subtract, I get 0. And when I add, I get 36. I do have an outlier. My outlier is 42. Okay. Any questions about that?